Hello, and welcome to ASL to Text, converting sign language gestures from digital images to text using Fourier Descriptors. I'm George Corser. Today is April 16, 2012. This presentation has 4 parts. 1. Background. I'll talk about sign language gesture recognition in general. 2. Foundation. Barkoky and Charkari presented a paper in 2011 on segmentation and thinning, and I used that as a foundation for my work. 3. Earlier work. Last semester I did some work in Canny edge dilation and used relatively real-world images, not perfect laboratory images, to determine whether the sign language gesture matched a test set. 4. My current work, and using Fourier descriptors to see if we can improve on the earlier work. Let's talk about background. Sign language gesture recognition, the concept as I define it, is basically a deaf person who is able to gesture into a telephone camera, and the telephone will communicate in audible English, and the person who's hearing can speak using audible English, and an avatar will return with the sign language gesture that the deaf person can't understand. It's basically similar to Talk to Me app, only for visual to auditory languages and back again. Perfect example might be the drive-through window. Deaf person comes up, he can't hear what's going on, but if he puts his phone up to the confirm order here box, it'll tell him what what do you want to order. He can order and gesture into the phone, and then the phone will communicate audibly to do his order. So that'd be an example of when you might use something like this. In a full-blown concept, we may well have a need for to go to the internet to get to more complex sentences. But right now, I'm just trying to do sign language, which we hope can be done right on the mobile device itself without going to the cloud. The problem is some of the letters of the American Sign Language ASL alphabet are hard to distinguish from one another. Now you can see some of these, it's quite clear, are very different from others, but if you look at a certain subset of them, you can see that they're kind of similar and the camera might not pick them up. So we're going to look at these especially. This is the last slide was a training set, this is the test set, different background color and so forth. Same problem though. This was done mostly in Matlab, this work that I did here. The basic piece of this process flow we're trying to uncover is sign language to text. There's, of course, obviously other pieces there, but most of them have been accomplished more or less. But the sign language to text piece still remains elusive, and we're trying to get to the point where it is ready for prime time. So the goal is to find an algorithm, find some method to convert an image from a picture, gesture, to the letter. I better get even a word. Part 2, Foundation. The foundation of this work comes from a paper by Barkoky and Charkari, and they show that you can use segmentation and thinning to identify the numbers of the Persian number system in sign language, Persian sign language. You can see that row A at the top is Arabic sign language, row B is American sign language, row C is Persian sign language. Again, the lower bar there, the lower set of black and white pictures show what happens as far as segmenting the image into a hand shape and then thinning it into a skeleton to find the endpoints and count them up, and that helps identify the numbers. Unfortunately, it does not work for sign language because, as you can see in line B, the purple line there in the middle of the screen, those don't have a consistent number. You can see that all of them, except for the one on the right, have 3 extensions, so the system won't work basically. But we can still use the segmentation part of the Barkoky process. So steps 1, 2, 3, 4, 5, and 6, we are going to use, or I use that for my work. 1, capture the image. 2, rescale it. 3, extract the hand segment using colors of flesh tones. 4, reduce the noise. Get rid of all the unnecessary spots and clicks and whatever in the picture. 5, crop it at the wrist as shown in the graphic at the lower left. And then you have the resulting hand segment in step 6. This is the Matlab code that I used to be able to achieve this. Not very fancy. Read the image, resize it, extract the hand using the color scheme. I did use a different color thresholding mechanism than what Barkoky used. That is an issue that needs to still be addressed, but it was fundamentally the same process. This is a histogram of the red, green, and blue subsets of the image in the upper left, and that's for the training set. This is showing the background is a very narrow little subset that makes this basically a laboratory photo. The hand part has a wider set of colors in it, and that's the middle bar of graphs there, and so those are histograms. Then in the training set, it's the same. Sorry, the test set is the same situation, although a different mix. But fundamentally, I was able to basically take the hand, flesh tones of the hand, out of the rest of the picture. Once I was able to do that, I reduced the noise. Basically, I filled in holes. You can see the last line of Matlab code is using imfill, using the holes there. I also closed any kind of shadows. As you can see in the upper left-hand corner there is the hand. The next picture to the right, you can see the shadows of the knuckles. In the third picture over, you can see those have been removed. I used a closing method for that. Same thing on the training set. Now, to identify the wrist position, I basically looked for a point, looked for a smooth spot, and assumed that was the arm, and then found a crook in the image, and that's where I counted it as the wrist. Basically, it searches the bottom to the top of the image, finds the leftmost pixel, and sets the wrist position of the first pixel that's off that edge. So here, like you can imagine, those dark blue boxes there are the edge of the arm. Once it hits a certain point, it starts going backwards. Bingo, we have the change here going the other direction, so we assume that's the wrist. That next point below there, we count that as the wrist position. So we've now isolated the gesture segment using the Barkoky method fundamentally. So that's up to step 6. These are some pictures of what it looks like. You can kind of see that the lower left-hand side shows skeletons, which were pretty much meaningless in this particular system. But the segmented image on the right-hand side, you can see, had some meaningful value. So these do not have the hole filling and closing, but that was done, so that these should be closed. Anyway, so the bottom line is I did use this Barkoky process to do the segmentation. Now, let's look at the earlier work. Earlier work, basically, I did the segmentation similar to Barkoky, and then I did an image comparison using various techniques. Basically, I took these thresholded images, the test set and the training set, and I just subtracted the errors. I took the test set and the training set, subtracted them, and whatever the differences were, I counted those as the count, I guess. So the bigger the count of error, the less likely that was a match. That was the idea. I used some other techniques, though the last one was a Canny edge dilation technique, where I took a Canny edge and dilated it, and that one seemed to be the most effective. Erosion Subtraction was one of them that I used. This is similar to the Canny edge here. You can see that there is basically just I eroded the image and subtracted it out of there so it has a hole in the middle, so it gives more, I guess, prominence to the edge of the hand. Canny edge here, you can see that in the Canny edge dilation, I dilated these images, but these are, the upper left is the Canny edge, and then the other ones are other edges. This is the Canny edge dilation Matlab code. Nothing fancy there. And the experimental results showed that the full threshold method was not bad, and plus it was really simple. So we were able to get 19 to 27% on that. Canny edge dilation, a little bit more variability there, but we got 12 to 35% on that method. So I'm calling that one my number one technique. Diced segments didn't do too badly either compared to the other ones, but when you look at this, none of these numbers are high enough to be satisfactory as a gesture recognition software package. We need more like 90% or 95%, not 35%. These are the matrices. A lot of times they, like take this one here. This one did match the letter, but it also matched another letter, so that didn't count really. I mean, you can't have it matching two letters because you don't know which one to pick. But so maybe it did better than 35%. Anyway, disadvantages of this system are the lighting conditions. Flesh tone backgrounds are hard to detect, which really is a continuing problem. It requires training for the specific user of the phone or the software. So it's got to be trained by the particular person, and the applications, of course, are limited. There's other reasons why this is different. But basically, the result of all this is I wanted to do something different that overcame some other disadvantages: translation, rotation, scale. These types of things are eventually going to have to be solved, or this whole opera falls apart. So the suggestion from Dr. Ciadat was Fourier descriptors, and he pointed me to the right place in the textbook about where that's discussed. So the current work that I've done this semester is in the area of Fourier descriptors. Now let's take a look at this. I'm going to talk to you now about Fourier descriptors as the concept, Fourier descriptor computation, the way I computed it in Matlab, and my experimental results. All the code and data is available on my website at the university. From page 818 of the textbook, we can see that the boundary of a given object can be defined as a sequence of coordinates. So basically, you can take a thresholded image and pick a bunch of coordinates that circumnavigate that image. The number of coordinates would be k, big K. Now, you can create a vector called S of k, which is basically a complex number, where you take the x coordinate and you add that to the imaginary constant I times the y coordinate. That will give you k complex numbers. The beauty of this is it turns a two-dimensional problem into a one-dimensional complex number problem. Pretty slick. Then you can take the Fourier transform of this, and you have some interesting properties as a result. The first coefficient of this transform is the centroid of the shape. If you set it to 0, it establishes translation invariance for the various images you're comparing. Pretty nice. The second one, A sub 1, is the size of the shape. It's basically a circle centered on the particular centroid. So if you divide all of the A sub u of this by A1, then you're going to get a scale invariance. Everything's going to be to the same scale, the unity, basically. And the bottom graphic, I just cut and pasted an image out of the textbook there. It shows the equation for this particular thing. It's just a Fourier transform. It's a discrete Fourier transform. Now, the other cool thing about this is you can choose a subset of the descriptors. You don't have to use all of them. You can choose some p less than k that gives you the Fourier transform. Well, it gives you a set of descriptors that can be basically restored to the original image or something close to it. On page 819 of the textbook, it shows an X chromosome, the outline, the contour of an X chromosome, using from 2,868 descriptors in the upper left-hand corner down to 8 descriptors in the lower right-hand corner. That's not bad. The only problem is it only works for smooth shapes. There are limitations, and I'll show you this in a minute. But basically, it's a very good way of shape recognition, which is basically the problem in hand gestures, recognizing the hand shape. And there's one more very cool thing. You can use these Fourier descriptors, you use the statistical moments to compare means and variances and so forth. So what we can do is we take the least square error and estimate the best match between the test set and the training set. That is pretty cool. So we're using the frequency domain now to evaluate the test set, training set match instead of just the morphological processing. So let's continue. We did 1 through 6 was the Barkoky method. Now we're going to do 7 through 11. That's the coarser method. 7, well, it's not really the coarser method, it's this Fourier Descriptor method. 7, we extract the edge, and it's 1 pixel thick. 8, we convert the 2D coordinates to one-dimensional complex number vector. 9, we compute the discrete Fourier transform of this vector. Then we create the matrix of differences, and we compare those square errors to see which letters match. Piece of cake, right? Again, I want to remind you that we did do the closing, and you can do rotation, and it'll be rotation invariant, so it doesn't matter how it's rotated. But I did do closing. You can kind of see that we lost some of the resolution in the closing. All right, so step 8 here. Convert the 2D coordinates into 1D complex numbers. There's your code. S of k equals x of k plus I times y of k, right out of the textbook. We compute the discrete Fourier transform. The very last line, we just used the Matlab code for that. I sorted out the angles to be so that they all came from the same basically place or angle, but I'm not sure it's necessary to do that. Anyway, that's what I did. And then the normalization, I divided all of the items in the Fourier descriptor vector by the second component. So we basically had a translation, scale, rotation, and starting point invariant set of Fourier descriptors. Then created a matrix of square errors, and then I calculated the differences between these square errors. Did it letter by letter. Whichever letter was closest in the test set to the training set represented the best match. Here's an example using 8 descriptors. I was able to achieve 19% of a match. Actually, even better than that if we counted the ones that had duplicates. This is actually the best method we had. Experimental results show for 2 descriptors, which is pretty much nothing, because it's just a centroid in a circle, 8%. Amazing that I was even that close. 6 descriptors got 12%, 8 descriptors 19%, 32 descriptors 15%, and I tried doing 1,024 descriptors, but that did not work. I could not get the computer. It took 2 hours to just do half of the set, so I do have some results there, but I can't attest to that. There's a video that shows this type of thing. It's on YouTube, and what it boils down to is it says here that just to get this edge here, they needed 629 descriptors and 692 to get one finger pointing up, and 1,027 descriptors to get 5 fingers, just the number 5, you know. That's not too hot, so I'm not sure. Maybe that's why my results weren't so good. I didn't use enough descriptors, but dang it, I thought the book said you didn't need to use that many of them. So I didn't do that. When I restored the 8 descriptor, this is the letter A restored using 8 descriptors. I didn't re-rotate it though, but that's not very cool. This is 128 descriptors. So, you know, not too impressive there. And then the computer vision, let's just leave that at that. The descriptor method didn't work well enough to be used on a phone. That's the end of that. Now, I've been keeping in touch with a guy named Christian Volger. He's the guy in the lower pictures here, the left and the right. He's, I think, one of the leading people in this field. He said to me that the way to statistical approaches and machine learning is the way this thing's got to be solved. That's his opinion. And he said that you got to use real-world images of hands and so forth, not just these laboratory conditions. But he said that's a very valuable project to be working on for a PhD. So I'm still pursuing this aggressively and keeping in touch with him. And you can kind of see that the laboratory image of the letter A on the right, which is not a perfect laboratory image, it's just a cell phone shot. But it really isn't as true as my own iPod there. You can see that the shadows and so forth, that's more what you're likely what you're going to get. And we need to probably do testing with even tougher images with even worse thresholding problems. So I'm not sure how that's going to be done, but that's where my future direction is going to take me. So image processing is the space that we've been studying, at this last 2 semesters, but Christian Volger suggests that machine learning is where the real work is being done, the real success is going to be. So I don't know if he's right or not, but that's what I'm hearing. The conclusion of this presentation is this. Real-world conditions present obstacles, tough obstacles. We need better threshold. We've got to be able to detect the hand more clearly and smoothly, or the whole opera falls apart. Either that, or we need more descriptors, so many more that it might not be handleable on a mobile device. Anyway, more work needs to be done either or on the software to make a simpler software system, or faster hardware so that you basically can run Matlab on a cell phone. Whichever way, as these 2 things converge, we will eventually get to the point where this is a viable tool. So again, future work, better flesh tone detection, maybe different algorithms. Could use a range camera to compute distance instead of finger shape, but there's so much. People have been working on this for a long, long time, and we're getting close now to the point where we can make some more headway. So we've only just begun. Thank you for your attention. Hope you enjoyed the presentation.